Pepe invited us in to talk to you guys today about torch safety, safe cylinder handling practices, that kind of stuff. If the only thing you get out of this class today is that the gas in this cylinder that looks like air and smells like air and tastes like air, you don't ever call it air again, we're ahead of the game. So what we're going to talk a lot about oxygen, and you'll notice that the label on here has got a yellow tag on it. Yellow typically means what? Caution, right? If it's a stoplight and it goes yellow, that means proceed with caution if you want to. Doesn't say danger. It isn't red, right? But this gas is probably the one most likely to cause an injury to you. And we're going to talk a lot about that today. So I can do a couple things here with this birthday candle. If I take my fingers and I pinch the wick, the air cannot get to the candle. The air's got the oxygen in it. Fire is going to go out, right? If I wet my fingers and I grab it, the moisture is going to take the heat out of the wick. Fire is going to go out. The third thing that I can do is restrict how much air it gets to burn. So the air that we're breathing is roughly 70% nitrogen, does nothing for us. 29% or 21% oxygen, sorry. You get those two together, we get to 99, and that other 1% is where argon comes from. So those three gases, oxygen, argon, and nitrogen, are what our atmosphere is made of. Talk my way right through the candle burning out. We'll light this other one. If I don't wave this around too much, I want you to watch what happens to this candle when I move the jar over. Went out almost immediately, huh? So what do you suppose caused that? No oxygen in there. Right now, if we had an oxygen analyzer, we could stick it in there, it's probably 14, maybe 15% oxygen, but not enough to keep the candle burning. So the one last thing that we'll do before we get into really what we're here to talk about, I'm going to take the torch, I'm going to push the air out of the jar, and I'm going to replace it with oxygen. And you'll notice that the fuel gas is off. I've made that mistake before. See if you notice a difference here. So, what didn't happen? Is there any kind of explosion? Any kind of flash fire? Oxygen doesn't burn. What it makes burn is anything that's already burning is going to burn much hotter and much faster. So in the case of steel, just in case you weren't aware, we can't use compressed air to cut steel. We use the oxy-fuel torch, oxygen and acetylene together, to get the steel to its kindling point, that cherry red color that we're used to. And once we hit cherry red and we hit this lever, we dump pure oxygen onto it, the steel actually becomes the fuel. And if you've ever thought about the biggest hunk of steel that I ever cut with a torch is a 16-inch riser at a foundry in Seattle. So same premise, it doesn't matter if you're cutting 1/4 inch or you're cutting 16-inch. You got to get it cherry red, and you got to have a big enough hole in here to keep the volume up so that it'll push all the way through that chunk of steel and come out. We got to have more than 85% coming out the backside or it won't go. So if your tip isn't big enough to burn through whatever thickness it is, it's a 1 inch or 2 inch or a 1/4 inch, if you're using too small of a tip, and you've seen it before where the burn goes part way through, and it comes up all frothy and it doesn't finish the burn. Usually we'll go crank the pressure up, right? First solution, but the correct solution is put the right size tip to start with. So by changing, that drives it. And you'll see that standard air versus the regular, quite a difference. Okay. So the way these cylinders are shipped to you, they come to you with a cap on it. Cap's there for a couple reasons. Number one, the valve that we attach our regulator to is made of brass. And the reason for that is that brass basically is self-lubricating. The same valve that you put your regulator on, that's how we fill that cylinder. So the connection, disconnect, reconnect, disconnect would wear out a steel valve, okay? The valves are threaded into the cylinder cap, but to protect this thing in transit and as the full cylinder stands there, the cylinder cap's put on it. And they come to you with different size holes in them. I grabbed 2 examples off your own rack. That one's got a giant hole in it. This one's got a round one. This one's got oval. Doesn't matter. The reason those holes are in that cylinder cap is in the event this thing gets caught in a fire, before the cylinder turns into a hand grenade, here's where our regulator goes. This is a burst disc right here. And when that cylinder gets to 3,000 PSI, that burst disc is going to let go before this becomes or ruptures, right? In the event that it's full and it's in your full rack, those holes are there to let that gas get out. That's the only reason they're there. The drawback to them, though, the bad part about them, is that those holes let all the dust and debris that's airborne in our work environment have access to that cylinder valve just through air movement. And it can be in our fill plant, on our trucks in service, in delivery to you, in your full cylinder rack as they stand outside. That airborne dust is everywhere, right? So the first thing you do when you uncork is, in particular, any high pressure gas, but I think oxygen's probably about the only. Do you use some nitrogen here too? Okay, nitrogen and welding gases at all? Pepe, got some welding gas? Okay. Argon, CO2, mixes, whatever. Unscrew the cylinder, point this thing away from you, momentarily just crack the valve. We don't care how dirty the outside of this bottle is. We care a lot about how dirty that inlet nipple is. And just by simply cracking this thing, and ordinarily, I would say we do this with 2 hands, right? We do it that way. We want to make sure that that's clean. And I got an example. Have you ever seen a gauge? This happens to be the operating pressure gauge on an oxygen regulator where the needle didn't go back to 0, where it was arbitrarily stuck somewhere. We got a couple guys that have seen that, huh? So Central Welding Supply has 25 stores. And I would venture to say that in each of those 25 stores, at least once a month, we see this come in on a regulator. It's the most obvious indicator that something's screwed up. And that happens because this adjusting screw gets screwed in and left there. We run the cylinder empty, we take the regulator off, we bring the full cylinder back in, we connect the regulator back up, we snap the valve open. Nothing high-tech about regulators. They're very simple mechanical devices. Half of this is designed to handle the pressure going to the torch. The other half's designed to handle the pressure coming out of the tank. And this thing, this adjusting screw, opens or closes the door between those two. So if this adjusting screw is screwed out, backed off, when we turn the cylinder on, we're only going to energize the high pressure gauge. If it's screwed in at any point, and like for this little example that I just did with my oxy-fuel torch, I had the pressure at less than 20. Even though it's less than 20, when I open that full cylinder at it and I hit 2,500 PSI on this side, before this simple guy can go, hold it, I don't want to let 20 out, I only wanted 20, we momentarily hit it with cylinder pressure and this gauge goes boink and it stops somewhere, right? So, broken. I'm going to pass this around in a minute for you to get your hands on, but there are 7 hairline fractures in this gauge surround. It almost came apart, but it didn't. The real reason I'm packing it is it shows an example that I've only seen in advertisements in magazines. Take a look at what happened to the back of the regulator. So what do we need to have a fire? Fuel, oxygen, and heat. At some point, fuel got into this. It was attached to an oxygen cylinder. So we got fuel and oxygen. Where was the heat source? Any ideas? Huh? Cracking it open. Okay? Exactly. So this gauge is at 0, and I snap it, and it goes at 2,000. That recompression, that's a heat source. That recompression ignited this. So I'm going to pass this around now, and I'll start at this end. But this has got a rubber diaphragm in it. And the rubber diaphragm is still intact. I'm not saying it's totally functional, but the rubber's still there. The brass failed. this happened so quick, the rubber didn't burn. So that's called a seat fire. The other thing I want to talk to you about the cylinder cap. Notice this lifting eye that was welded on here? A guy actually got a merit award for coming up with a good idea. Somebody told him that if you did that, we could then use the jib crane to pick the cylinders up and put them onto the service truck. It would save a back injury. You absolutely don't want to do that. You don't want to lift by that adjusting screw. That cap screws onto what's called a neck ring. This happens to be a unmarked neck ring. And I'm saying that only because if you're at a garage sale and you're looking for a set of cylinders for home, or the guy's got a set of cylinders he's trying to sell, and it's got somebody's name on it, like this one does, it says property of Pacific Welding Supply, you can't buy it. Or you can buy it, but when you go to fill it, they're going to take it away from you. So if you're looking at a set of cylinders and it's got a blank neck ring on it, that's a private. That's a customer-owned cylinder. You can take that, you can pay that guy whatever he wants for it, take it to any distributor and they'll fill it for you. But, so this neck ring, for example, they don't know when they make the cylinder who's buying it. So these neck rings sit on the shelf with Pacific Welding or Central Welding Supply on them. We place our order for bottles, we get 1,000, they put our neck ring on, it gets locked onto the cylinder and off it goes. It's not an integral part of the cylinder. So it used to be in the old days, they used drift pins. There were 3 areas here that they'd lock this onto the top of the cylinder. Now what they do is they just round the very top portion of the steel shell to lock that in place. But have you ever had trouble unscrewing one of these? They cross thread, huh? Fine threads. Crazy. Almost impossible. You can cross thread these so easy and it feels like it's screwed on tight, and the first time it gets hit, it just pops right off. So if you've got to make a pick, if you're going to load that onto a truck, they weigh about 115 pounds, so that's a 2-man pick anywhere, right? Make sure that cylinder cap is fully engaged. Make sure you can turn it, lock it all the way down. One of you can use that as a handle. The other guy can grab the other end of the bottle, lift it up to height and slide it on. Leave this on as you're in transit. These things, a little moisture, fine threaded neck ring, fine threaded cylinder cap, a little moisture, and tomorrow they're rusted together. So it happens to be why I carry this crescent wrench, because it fits in that small hole. And you usually, a couple of shots like that and just a little twist and you can pop the thing free. Oxygen cylinders, we'll talk about the construction now. Oxygen cylinders from top to bottom, a steel 1-piece shell, 3/8 wall thickness roughly on the bottom. As we taper here, thickest part of the cylinder is probably right about here, and we're at 1.25 inches. And then that tapers down to where this 1/2-inch valve is threaded in here. These cylinders are tested to make sure that they're safe to refill every 10 years. And this particular bottle, I looked at it earlier, was first put in service in July of 1999. It has a star, or a plus sign and a star on it. Its first retest occurred in December of 2009, so 10 years after 99, right? And if the cylinder's full, it can sit forever. When the cylinder goes empty, that's when it gets retested, right? So the dates they aren't exactly 10 years because maybe it was in somebody's garage or barn. The last time it was retested after December of 2009 was in 2 of 20, February of 20. Again, a plus sign and a star. Those 2 indicators, that plus sign tells us that the cylinder, chromoly bottle, expanded perfectly, so we can overfill that cylinder 10%. The star is put on there only if it meets all the criteria of expansion, and it, again, is good for 10 more years. So those those indicators are key. And believe it or not, what happens, these cylinders, they expand like a balloon. So what's called a hydrostatic test is used, and the bottle is submerged into a pipe full of water. attached with a high pressure hose. The pressure in the cylinder is brought up to roughly 3,000 psi, and as this cylinder gets pressure, it stretches, it gets bigger, which causes the water to flow out of the pipe. And by measuring how much water it displaced, they can tell how much the cylinder expanded. And if it expanded acceptably, it gets the star. And it's good for 10 more years. If it doesn't make it, then the cylinder gets put into, typically goes to CO2 service first, because CO2 is the one gas that's liquid that has a maximum pressure of like 850 psi in the cylinder. So it gets degraded from oxygen, nitrogen, argon to CO2. And any kind of arc burn or a deep scratch in the side of the cylinder will adversely affect its ability to expand. Most of the time what will happen with these guys, it happens more so probably on argon cylinders in TIG applications, where a guy will hang his TIG torch over the flow meter and you will get a little arc off the top of it. But we've seen it come back from industrial customers too, where the guy hung his stinger off the welding machine over the edge of this thing with a piece of welding rod in it, and the welding rod arced in it. I even had one we found where a guy welded his name in the cylinder, put his last name on it, customer owned bottle. So it didn't cause the cylinder was full, by the way. Didn't cause a problem there. Where it's going to cause a problem, it's going to kill our filler, right? So if we miss that, or that little tiny arc burn is that's tougher to spot. But our drivers are trained to look for that kind of stuff as they roll the cylinders out, any kind of discoloration or whatever, because that's where that cylinder is going to break. When it goes to expand and it can't stretch, it's going to pop and it'll break right there. So, tough times. Okay, so this cylinder is good to go. We've made sure that it's clean. We can now attach our regulator back on it. Fuel gas is a different critter. This is a 10 cubic foot cylinder. I know you've got a little 20 cubic foot oxygen out there that you run, so I'm guessing you've got a portable torch outfit, maybe with it in a cart, or a little, pick it up and climb a ladder with it if you had to. So that uses this MC, but this is a cross section. So from top to bottom, where we talked about this guy's hollow, wall thickness 3/8, huh? This guy's not hollow, wall thickness is like 1/8. And from top to bottom, it looks like it's filled with cement. This is actually what they call calcium silicate. And every acetylene cylinder has this exact fill in it. The older style one actually had bits of charcoal. You could see black spots in it. But the newer design is like this. Every acetylene cylinder, once it's welded up, the steel shell is welded, gets this stuff put in it, and it occupies about 10% of the bottle. They then put it in an oven, and that rises like bread dough till it actually will blow out the top of the valve, because the valve's not in it, right? It blows out the hole, and then I'll pass this around for you to look at, but you'll see where they stuck a reamer in there, and they cut out the porous filler so that when the valve threads in, the valve drops right into a pocket of this porous filler, made specifically for it. Then the last step before it gets gas put in it is this stuff gets roughly half filled. It's 44% is the number, and those Victor books that I gave you, if you read the first 27 pages, they'll talk about the design of this thing, but that acetone saturates and filters through this porous filler. And it's actually the acetone that allows us it absorbs the acetylene gas. So, but it does it very slowly. We can't force it in there. This cylinder takes 7 hours to fill. This cylinder takes 7 hours to fill too. This tank holds 10 cubic feet. This one says it's got 129 cubic feet in it. Which one do you think is going to cost more? You got the same amount of labor in it, right? This little 10 cubic footer, we got 8 hours of labor we got to hide in there. And it holds this. There's 12 of these inside that one. So the price will be cheaper here, right? Absolutely, it is. Where the problem comes into play, it takes 7 hours to go in here. It takes 7 hours to come out too. So if we took that cylinder, if we took that one out in the parking lot and uncorked it and opened the valve and just let it blow, the gas can't get out of here any faster than that. It's got to sit, the gas has got to work its way through this porous filler. It's got to shed itself of the acetone, and then it's going to blow out. And this is one of the easiest things if you want to find out if I know what I'm talking about. All you got to do is take one of your full bottles and lay it down. And let it lay down like, I don't know, where do you live, like half hour from here? Pretend you're driving home to your house with it. Stand the cylinder back up, take the cylinder cap off, point it away from you and crack the valve. And what you're gonna see come out of there is a mist, a fog. That fog is liquid acetone. So where this thing's half full when it's standing up, when you lay it down, half full goes this way, right? And it's 44%, but what happens is when you stand it up, if you don't give it 30 minutes for that acetone to settle back into the bottle, when you crack the valve, it's gonna blow acetone out. And that acetone, by the way, if you've ever used it, and you probably have in the mill at different places, very corrosive cleaner. I mean, it's awesome cleaner. Cleans about anything. But it also eats the inside out of the first thing it goes through is your regulator, or your acetylene regulator. So if you've ever seen one of these, that you set it to 5, and over the course of 25 or 30 minutes, it goes to 7, it goes to 10, it goes to 12, it keeps going up. It's because the acetone has dissolved the seat assembly in the regulator. If it gets past that, then it goes into the hose itself, and you'll see issues with, well, it can cause any number of issues, but it can backfire, lots of problems. So acetylene is unique in that way. Acetylene, because of the way it's, well, we can take an oxygen cylinder and stand it upside down and use it, no problem. Lay it down in the truck, no problem. Acetylene has to be stood up. Now, where this guy has a burst disc on it, acetylene cylinders on either side of this cylinder valve right here on top, you'll see our 2 bolt heads. They look to be bolt heads. They're actually fuse plugs. Just like our automobile engines have in them, in case you forget to put antifreeze in, and we get into cold weather, before the block cracks, hopefully, the fuse plug gets pushed out. That's how the acetylene cylinder takes care of itself when it's in a fire or exposed to a fire. This particular regulator is a good example. Tell you a little story. This particular regulator was attached to a number 5 acetylene bottle, which holds 450 cubic feet. So if you're doing heavy cutting or you're running a big rosebud, you'll use the number 5 cylinders. This is the number 4. And typically we call it a 150 cubic foot cylinder, but you'll see on here that it shows 129 is the actual contents of that one. We'll talk about that in a bit. But the acetylene cylinder in this case was attached to a number 5 bottle, and the operator was going to bring in a casting. He had a lot of grinding to do, and the cylinder typically stood by his workstation. So he purposely buttoned things up and rolled it down to workstation number 4 and came back, used the crane to load the grinding, the chunk he needed to grind onto his work spot, got tooled up, got his face shield on, hard hat, gloves, the whole works, and started grinding on it. Operator from station 4 comes back, goes, hey, what's the torch outfit doing to mine? It belongs up at station 1. So while station 1 operator's working away like crazy, the operator rolls this thing right back where it was, in his work zone. Well, he's grinding with a 4-inch cupstone, 6-inch cupstone, hogging steel like crazy. And what was happening was his slag stream off the casting was going on top of the acetylene cylinder. And eventually he got so much slag on there that it melted the lead out of the fuse plug. And the next time he directed the slag stream over, it ignited the gas. And it had a fire going like 30 plus feet in the air coming out of that acetylene bottle. You can't stop it now, right? No valve, it's a fuse plug. So 2 things, you either put it out and then you can't see where the gas is going because it's going to burn somewhere, or you let it burn. So what they ended up doing, they threw a chain around the cylinder cart and drug the cylinder out in the parking lot and just let it burn. Fire department, they had 7 fire engines there in like 4 minutes. Machinist Inc. in Seattle. This regulator was screwed into that acetylene bottle, and as the fire was rolling out of there, it melted the gauge, and I've been carrying this thing 30 years, and the plastic from the gauge has not come off yet. When you turn the cylinders on, guys, I want you to use 2 hands to do it. We cannot eliminate the heat of recompression. When that gauge goes from 0 to 2000 or 2300, it's gonna go. But if we can delay that by milliseconds, it dramatically reduces the amount of heat we generate, so the likelihood that something's gonna catch fire or that we're gonna have a problem drops way down. So we wanna do it slow, 2 hands, crack it, let it come up to where it stops moving, and then open the cylinder wide open. We don't know, the torch apparatus doesn't know what material thickness you're cutting. And as an operator, we want to have access to what's in this cylinder as fast as we want it, as fast as we need it. And that's why this valve should be opened wide open. In the case of fuel gas, whole different critter. So what we're going to do, we're going to use 2 hands again to crack this valve. We're going to do it slow. And sometimes you have to move this like almost a quarter of a turn before this needle starts to move. Still not there. I know it works. Okay, so it's going to come up to 150 roughly. At this point, I'm already almost a quarter open. In no case open this more than 1 full turn. Just like your propane on your barbecue at home, fuel gas have coarse thread valves. High pressure cylinders have fine threaded valves. So we got to turn just because we're bucking the pressure, we got to turn a lot more times to get this one open than we do the fuel gas. And just like propane, this thing will probably go full open in 3 turns, 2.5 turns. But 1 is all we want to go. The problem is we can't get the gas out of the bottle. Opening this more than 1 turn doesn't open the valve any further. It is wide open at 1 turn. So, in this case, at that point, we can set our pressure. I'm going to back my oxygen down. Okay, in most shops, this thing gets turned on, and could be on all day. And 5 or 6 people could come use it and leave it back, still turned on, but not being used at the moment. The best thing that you can do, because to make sure that when you grab your striker and you hit this thing, before you grab your striker, crack the valve, count to 3 or 4, shut it off. Go to the other valve, crack it, count to 3 or 4, shut it off. What we've done is we have purged these 2 lines now. In the event that something happened to the guy ahead of us, maybe he ran out of oxygen, he didn't tell you. And before he could change the oxygen bottle, we had acetylene go back on it. Now this is your torch, and you've got a set of devices right here that are called flash arresters. And in part of that flash arrestor is a check valve. So could the gas flow backwards? Not likely. Do they ever screw up? They can on occasion. So, but by purging the 2 valves, what we know is that we grab our striker, we crack that thing, all we're lighting is fuel gas. There's no chance of it being fuel gas and oxygen. And acetylene is unique in that it tells us, see that indent right at my finger where the flame kind of flares out? Ideally, we want that 3/4 to 1 inch off the end of the tip. And if we do that, for this particular tip, that's the right volume of gas. We're feeding it right. You'll notice we've got very little black soot in the flame. If I choke this back, you'll notice the black soot appears immediately, right? That means incomplete combustion. So again, get it back to like the 3/4 to 1 inch off the end of the copper. And at that point, we turn the oxygen on, and we can pull this thing down to a neutral flame. Slightly rounded blue cone, right? So that flame is ballpark 6,000 degrees. I'm not going to argue with you. Is it 5,700? Yeah, it's probably closer to 57 or 58. But people say it's 6,000. when you're burning it correctly, if you look at that blue cone, appears to be sitting right on the end of that copper tip, doesn't it? And I've got my fingers like 3/8 of an inch from that blue cone. What we can't see is that when you light it the way I just showed you, we set the right amount of volume of acetylene, and then we turn our oxygen on. There's an air gap that exists between that blue cone and the end of that copper tip. That's the only reason I can hang on to it like I am. That air gap's an insulator. So when you light it correctly, everything goes cool. If we back this thing down, a little quieter, huh? Do you mind walking up here? I want you to take the torch from me, and I'd like you to pick a spot and just hang on it, let me know. So what did I do? Did I go to the regulators and change pressure settings at all? Getting warm?
Already, yeah.
Okay, slide back a little bit. What's happened now, all I did was starve the thing for fuel, right? Now that blue cone is sitting right on the end of the copper. And the longer that it runs, the hotter the copper gets. And what do we need to have a fire? Fuel, oxygen, and heat, right? It's going to get to a point, thanks, hot, huh? Okay, it's going to get to a point it doesn't need to come out of the tip to burn because the dang copper's hot enough to ignite it. The other indicator that you'll spot off, that popping sound, you ever heard that? That's a backfire. And what happens when it backfires is it's looking for fuel. And that fire will run back through this torch, and hopefully it's going to slam into these two things. But in the process, it kind of leaves a trace. And you can see if you've ever had that happen by looking in the main throat of the cutting tip. In between the O-rings on the back end of the tip here, the black soot. That black soot is there, that's unburned acetylene that's stuck there. The other place that you'll see it, this is your cutting assembly, is in between those two O-rings. So that I knew before we had the class, you've had lots of backfires. And I don't know if you run heating tips, rosebuds, do you on occasion? I think I heard that you did. Okay, so now we're going to do the main reason that I gave you the books. There's a whole bunch of reasons, but the first 27 pages, like I said, tell you what we're basically reiterate the class we're doing right now. But I'd like you to open your book, please. No more than 1/8 of an inch in, right? If you go more than 1/8 into this book, you're changing languages on me. I can't help you. So look for page 943, and it's going to look like that. Need one? You guys get them? We got more. 943. It takes a while to find them. So at the top of page 943 is a deal that says MFA heating nozzles. Everybody find that? Still got some that are looking for 943. The tip that you guys run is a number 8. So let's drop down to tip size, far left-hand side, tip size. Drop down to number 8. And it tells us that our acetylene pressure should be what? 10 to 15, huh? For a rosebud? Tip size 8. Get it?
Yep, 10 to 15.
10 to 15. Okay. Our oxygen pressure 20 to 30. Okay, that's probably in line. Here's the killer. Acetylene cubic feet per hour. The minimum for a number 8 is what? 30, and maximum is, okay, so let's go back to where we started. This cylinder, 1/7 of its capacity it takes 7 hours to fill it. The most we can pull out of it's 1/7. This cylinder holds 129 cubic feet. I'm going to make the math easy. I'm going to say that's 140. You got one empty cylinder that we just traded out today, actually had 140 on it. 1/7 of 140 is 20 cubic feet. That number 8 rosebud wants how many cubic feet? Minimum? Minimum 30. So brand new, full cylinder. We haven't even lit yet, and we know we're going to be starved for fuel. Because we can't give it, this bottle won't, At 129, that number is 18.4, Kevin, is that what you said? 18.46 is 1/7 of 129. So let's talk about this bottle that I called a 150. How come if it's a 150 is there 129 cubic feet in it? Well, if you look at the cylinders in your rack, you'll find that they go all the way down to, I think I saw a 109, there's a couple of 110s, there's 118s, 129, 140. It has to do with the acetone content in the cylinder. So when it's full of acetone, that's when the cylinder will hold the most gas. And if that were a brand new 150, perfectly full of acetone, it's going to hold 150 cubic feet. But we deliver it to you guys, and you put your Behemoth number 8 Rosebud on it. And it backfires like crazy, but we use it anyway. I got the mixer for the wrong. I want to show you. So you saw how hot that welding tip got, how quickly it got hot, I should say. The backfire that occurs, we talked about, will always go to it's looking for fuel. It finds the fuel at the mixer. And the mixer is the part right there on a welding tip, or right there on a Rosebud. In functional condition, this thing's got it looks like a drill shaving sticking at the end. It looks like a line across the center of it. But it really, it's a twisted drill shaving. It's probably got 4 turns in it. And its main purpose is to swirl the oxygen so that when the acetylene comes in between here, the acetylene gets blended well with the oxygen and it comes out of the mixer uniform to the head. That number 8, the reason it was called an MFA, multiple flame acetylene, there's 12 holes in a Rosebud head. That's where the MFA deal comes from. So with those 12 holes, if we starve it for fuel, it will backfire to here. Victor cutting assembly, very similar to yours. Mixer in this lower tube, backfire, took out right there, right? So backfires to the mixer. It will burn all the way back through here if it goes long enough. But in the process, yeah. So what you want to do with that guy, in the event that you have to do, you're using a Rosebud, you're number 8. We don't have access to a number 5 cylinder. All we got is 4s, right? When this thing gets hot, all we got to do is take the heat away. So turn the torch off and shove it in a pail of water. It's all copper. It's just going to get cold, right? And if you do that, when you go back and you light it correctly, you get for that 3/4 to an inch off the end of the copper, and you add the oxygen to it, and you go back, you can run again. And keep in mind, I'm not pointing this at a piece of steel. I got no reflected heat on it. But if I point that at something, this is gonna get hot faster because it's got fire coming back on it. So the same is true. When you go to shut these things off, because we need what? Fuel, oxygen, heat, right? If this thing starts making a noise, or your Rosebud is going, turn off the oxygen. The fire cannot burn in your tip without oxygen. It's going to come out of the front end of the torch, and you can turn it off. When you shut your Rosebud down, if you turn it off that way, it will never backfire on you again. You'll never hear that kapow sound. Turn off the oxygen. Now, people say, well, the fire doesn't go out. Well, it will. After we turn off the oxygen, get control of the fire, and then shut off the fuel, it'll go out without even making a spark. So, 3/4 to an inch, add oxygen, get it neutral. Again, she'll burn for a long time and not turn off the oxygen, turn off the fuel. It does 2 things for you. I usually put my torch on, but yours worked. Mine leaks. So what happens with mine is when I shut mine off, I've got a little tiny, it's smaller than this, flame at the end of my tip. because my acetylene valve leaks. It's good to know that, right? Number one, we know the valve needs to get sent in for repair. Secondly, if we know this thing leaks, we certainly don't want to leave the acetylene on, because it's going to leak acetylene into wherever we are, workspace, and it's combustible. So we don't want to do that. Okay, here's another example that we talked about, but we didn't talk about it much. We talked about acetone getting into our hoses and what happens when you run out of gas. So what I've got here is a section of twin hose. What I'm holding on to is, believe it or not, it's the red one, because it's got the left-handed nut on it, so we know it's fuel. And what's blown up here is the oxygen hose. How does oxygen blow up? It doesn't. So what had to have happened? Typically in a cutting process, we've got oxygen set at, I don't know, 40, 35? Our fuel gas is 10, somewhere around there, huh? So very unlikely that 40-pound oxygen is going to come up against a 10-pound fuel gas line. Nothing's going to happen until you run out of oxygen. So when you run the cylinder bone dry, our 40 goes to 0. Now our 10 psi acetylene, it's 10 against nothing. 10's going to win. It'll back up immediately. That's why I say the best thing that you can do before you grab your striker, always crack the valve, count to 3 or 4, shut it off. Grab the other valve, count to 3 or 4, or hit the cutting oxygen trigger, count to 3 or 4, and then grab your striker and light it. This guy did not do that. So his acetylene, before he noticed that things had gone south, his acetylene had backed up into his oxygen line. He changed the cylinders. He opened the fuel gas valve and lit it, and it lit just fine. And he opened the oxygen valve, and all of a sudden, kapow, the hose blows up. Because he didn't purge the acetylene gas out of there. It had acetylene oxygen mix in it. It burns at 6,000 degrees in a hose. How long is a hose going to last at 6,000? Not very long. It vents, right? Now the other problem that you can run into with oxygen, and it happens many times, and I'm a big proponent for FR clothing and cotton clothing as opposed to nylon or any polyester blend shirts or whatever. It's very common to have a hose leak occur right here where these two valves, because number one, we're pulling on these things. We bend these severely. The nipple actually protrudes beyond a little bit beyond the ferrule here, and it's just a weak spot. And if we've got oxygen leaking here, that oxygen can saturate our shirt sleeve. And if you've ever seen, man, I called in the shipyards for 35 years, and I couldn't tell you how many guys I've watched take a cutting torch with the oxygen. It's air, right? Crank it up to 40 or 50 and blow the dust off your clothes. I had a buddy of mine, he got permission to knock off a few minutes early one day for his wife was going to come pick him up. They're going to lunch. So he cleaned himself off with the torch, and as he was walking out of the shop, one of his buddies, one of his co-workers, welding with 7018, you know, every once in a while you get that stinking flyer that'll come off the stick electrode, hit his shirt, and just that fast, from his belt line up, he was naked. His collar was still on his neck, his shirt tails were still stuck in his pants, but the body of his cotton shirt, summer day, gone, complete, along with his mustache and his sideburns. That oxygen doesn't burn, but if you get it trapped between your skin and a cotton shirt, it's going to burn. And the oxygen is what took out his mustache and didn't burn him bad, but scared the crap out of him. So don't ever use oxygen as a substitute for compressed air, right? Oxygen is not air. Which leads me to my favorite tool. Anybody know what that might be? Die grinder. Okay, what kind of die grinder? Is it electric die grinder? Pneumatic. How do we keep pneumatic tools alive? Oil them, right? Every day. Everybody knows, hey, before you leave the room, 4 or 5 drops of machine oil, you're good, probably good for the rest of the day. Company called Washington Iron Works in Seattle, now the site of the Ryerson Bus Garage for Metro. Operator spent 40 minutes adapting his Chicago pneumatic, everybody in the world knows that's an air fitting, to an oxygen pipeline station valve. He cracked the valve, it looked like air, smelled like air. Hey, gotta be air. Funny, nothing fits it. I mean, you can't go into McClendon's and get components to fit on an oxygen regulator or that nut to put on your oxygen bottle. They don't sell them. You have to go to a welding supply house, somebody that specializes in welding stuff to get. So 40 minutes later, he jury-rigged a whole series of convoluted connections so that he could get his two-prong Chicago pneumatic fitting to lock on. He got the female on the pipeline and he coupled them together and he hit the go button, and for the first time in his life, this is what is a forward exhaust die grinder, right? So sometimes they blow out the back. This one blew out the front. First time in his life, he hits the button, fire goes flying out the front end of his die grinder. He's on 6 foot of hose between him and that construction. He dropped it. I'm in the shop. I'm on the other side of a wall that's about 30 feet tall, stops 3 feet short of the ceiling between him and me. All of a sudden I see this bright flash, no noise, just a blue light. Remember those little Kodak cameras they used to make with the square flash cubes on them? That you're at a party and you could tell somebody's taking pictures because all you saw was the blue light going off, right? And then they rotate and you could go again. So a guy hollers, "Hey Tom, one of your cylinders blew up." And I'm thinking, hey, there was no noise. I mean, I didn't hear any noise. So I go peeling around the corner. I'm thinking, this ain't a cylinder. Run around, I gotta go 60 yards to get, he's 30 feet from me, but I gotta go 60 yards to get around the corner. So I find him, that thing's laying there. The smoke is rolling off of it. He's staring at the ground. He's got a hard hat on, face shield. He's got Nomex green Nomex fire suit. He's got welder's gloves. Everything's cool, except this thing's laying at his feet. I'm thinking 911, right? There's like 1.5 pounds missing out of this die grinder, and he was within 3 feet of it when it went off. He didn't get a scratch on him. Didn't get hurt at all. So what happened? I was able to find these 2 pieces, and I found the go button that was spring-loaded that belonged somewhere in here, and I've lost that part. But these 2 were intact, and that's my oxygen compressed air story. If you didn't believe any of the other stuff about oxygen exploding, believe this one, and I'll pass this around for you to take a look at it. It's kind of cool. One of the neatest things that I found early in my career, the guys that taught me initially how to do these safety meetings gave me a tool. Tool is a heavy wall piece of stainless pipe with an oxygen nipple and nut on it and a silver brazed slug at the end to demonstrate the heat of recompression. So like 50 sometimes I did this demo with a group just like this. Take the oxygen regulator off, and this will screw right on here. For a fuel, I used a book match. So I would either drop the book match in here, or I'd unscrew this slug at the end and drop the book match into this end. And under this high-tech Bic ink pen clip, I'd put another book match. And it didn't matter if it was here or there. It didn't matter where on the tube that I located it. As long as the cylinder had 800 PSI left in the cylinder on the high pressure gauge, every single time, by simply cracking the cylinder valve. Remember we talked about I want you to use 2 hands to open these? Well, this is why you don't do it single-handed. But every guy in this room is strong enough to one-handed crack that valve open, right? But every single time, it would ignite the match inside the tube that transferred enough heat through this heavy wall stainless. It's heavy wall. You're not going to bend this thing. It'll light the match on the outside as well. So demo number 60, my group of 15 are all gas welding instructors. And we're in Boise, and this class that we're going to knock off in an hour, we're doing in 4 hours. So I'm telling lots of stories about diesel engines that guys tried to use an air compressor and they ran out of air, so they refilled the air compressor with oxygen and hit the go button on the diesel and it blew up. So anyway, I tell everybody, okay, I want you to watch what's going to happen here. And before the class started, I forgot this part. Before the class started, just like I did here today, I checked the cylinders to see what I'm working with. And the high pressure needle went to 3,000 PSI. The cylinder was overfilled, way overfilled. 2,300 typically. It's 70 degrees, that's where we want to be. We're in Boise. I don't know, maybe it was 80 or 85 degrees. That'll inch the pressure up a little bit, but not a lot. It was overfilled. So I'm thinking, hey, I know what I hunt, I reload, I know you get debris built up in your barrel. That's why you have cleaning rods, right? So I pull a plug out of this thing and I look through it, oh man, it's filthy. So I get a piece of t-shirt and a piece of TIG rod and I push that thing through and it comes out black, and I push it through like three more times. Now I look in, it's clean as a whistle. Okay, I know what I'm doing. So we get to this point in the class, I throw my book match in, I'm being all smart, I go, okay, I want you to watch that one on the outside, and I go, pew, like that. And from right here to the floor, I got a 3-foot wall of fire screaming out of this thing. In fact, it took the cylinder and it rocked the cylinder back. Right at the tip of the Bic ink pen, you're gonna see a pinhead-sized hole. You ever tried cutting stainless steel with a cutting torch? Can't do it, can you? Doesn't burn. This thing wouldn't go out until I shut off the oxygen. I had to walk back over to the cylinder and shut the valve off to make the fire go out. So what happens when you destroy a book match? What's left? That little head, right? That piece of carbon that doesn't completely burn. It blew that thing right through the sidewall of this thing and got the whole process rolling. So the heater recompression is a real deal, and I haven't demonstrated it since this demo in Boise, Idaho. If you don't believe me, I'm sorry. You're stupid. It's a real thing. At this point, we're going to shut the system down, and I'm going to pick the fuel gas valve first. You'll see that thing will eventually drop. High pressure goes down first. Eventually, this one catches up with it. At this point, I'm going to back that adjusting screw out until it's free turning. And then I'm going to close this valve. We'll do the same thing with the oxygen. Open it up. That goes to 0. That eventually goes to 0. Back this guy off. System is totally shut down right now. And at that point, you can put it away. On behalf of Central Welding, Pacific Welding Supply, thank you for your business. Thanks for being great customers, and please be safe.